Alright guys, let's take a look at lab number 3. This again is an inductive sensor. We're going to take a look at the M18, and we're going to look at how different metals affect the sensing distance of that sensor. And then we're going to take a look at the correction factor for each of those metals. So the application for this guy that Festo has given us is that we're doing a lid inspection, and as they're going by, we're just making sure that each lid has the appropriate metal that has been used. Okay, and we look at the setup here. We're grabbing the M18. That's the larger of the inductive sensors in your unit. Drop your M18 down. Then you're going to put the positioning slide in, and again you're going to butt up the piece of metal up against the sensor so that there's no distance between the sensor and the piece of metal, and the back of the plate should be at 0. That way any distance that the back of the plate moves, that means that that same distance will be between the front of the sensor and the actual piece of metal. As we take a look at how to wire this bad boy up, we've got a 3-wire sensor, so we've got 24 volts. We've got our common here to provide it with 24 volts. And then with this one, Q1 is the output going to the light bulb. Again, out in the field, the positive is going to be the brown, the negative is going to be the blue, and then regardless if you have a PNP or NPN, this guy is going to be black. But we can see that this guy here is a PNP. It's a sourcing output, in that the common is already connected to the light, and the sensor right here is providing a source of positive current to the actual light bulb there. So this is a PNP or a sourcing output. As we take a look at here, we need all these different pieces. So we're going to need the galvanized steel, the stainless steel, brass, aluminum, and copper. So 5 through 9 in your tackle box there. And for each of those guys, we're going to look at the switch on point and the switch off point. The difference between these guys is going to be our hysteresis. As we follow down, we're going to use the correction factor, which is found in the Allen Bradley textbook on page 4-7. And this M18, if we take a look at the cut sheet, I believe it's good for 8 mils. So we're going to use that correction factor, or that percentage of 8 mils, and we're going to see how close it is to our values that we have up here. Alright guys, let's take a look at the setup here. So we have 3 different inductive sensors that are available in the shop. So we have the M12 that is non-shielded, and this one is just a discrete output. It provides 24 volts or 0 volts. We're going to get rid of this guy. This guy is also an inductive sensor. This one with the threads all the way to the end is a shielded. It's an analog output. It provides 0 to 10 or 4 to 20 milliamps out. We're going to get rid of this guy. This is the one that we need for this lab. This is the M18 inductive sensor. M18 in that the front face of the sensor is 18 mils across. Okay. So first thing we need to do again is we're going to take our output here. Now you guys have 24 volts in the shop that you can just hook up to. I'm going to set my output here for the DC output, so I'm going to click on this guy. Just go back up. There we go. And I'm going to crank this all the way to 24 volts output. These sensors work off of 24 volts DC. Excellent. Okay, so now we got 24 volts DC coming out of this guy. Variable DC output, 0 to 25 volts with 0.3 amps max. Alright, let's set this bad boy back up again so we can see what we're doing. Okay, now with this M18, we need to provide this guy with 24 volts. So let's take one conductor, and we'll go from our common to our 0 volts of the sensor. And then we'll take, let's try a red for our positive here. No matter how hard I try, these guys always get tangled up. There we go. Okay, so now we've got our positive here to the sensor. Now some sensors out in the field are going to have LEDs that turn on right away to tell you that it has the power. Ours do not. Then we need to have the output. Remember, the output is Q1, right? So we're going to go from Q1, and we're going to go to our light. Let's just move this in closer. Sun is shining down, gorgeous day. There we go. Okay, looks good. Okay, let's move this here so we can actually see the light turn on. And then we need to finish off this circuit. We need to provide a path back for the light bulb. So we're going to bring that guy back to our common. Doesn't matter which common we're going to, it's all the same wire. Beautiful. Okay. Next thing we need to do is we're going to take the galvanized steel, number 5. So we're going to open up our tackle box. Okay, so again we have our tackle box here, and within the tackle box is everything we need. Right, so we got all our pieces here. Again, disgustingly organized before and after your labs. And I need number 5. Because it's organized, I can just grab that bad boy and drop it right in. Okay, what I'm going to do now is I'm going to put the back of the unit at 0. And now I'm going to take this and I'm going to jam this right up against the sensor. And you can see that the light is on. Okay, if you've grabbed the wrong sensor, then this will be very, very dim because you probably grabbed the analog sensor and it only puts 10 volts out. These lights need 24 volts to fire on with full brightness. Okay, excellent. So now we've got 0 mils, and now we're just going to look at our travel with our turn on and our turn off point. Okay, so what we'll do is we'll push this guy back now that we have everything set up, and we'll just, there's a thumb wheel here that we can just slowly bring this in. And that is 10 mils, 9 mils, 8 mils. Remember that in the cut sheet it said around 8 mils it's going to turn on. So 8 mils it turns on, and at 9 mils it turns off. So we have a switch on point at 8 mils, a switch off point at 9 mils, and a hysteresis of 1 mil. Again, you're not going to see all that far with an inductive sensor. Remember, as soon as you power it up, there's a magnetic field that expands and contracts in front of it. Once it cuts across a piece of metal, it induces currents on the front face of the metal. Those currents create their own magnetic field, distort this guy, and there's an op-amp circuit there to fire on the transistor output. Okay, so that was the galvanized steel, number 5, and we found that it had a switch on point at 8, switch off point at 9. We're going to now switch to the stainless steel now, and we can see that at about 9 mils, nothing's happening. So let's see what happens here. 10, 9, 8, 7, 6, around 5 mils it's turning on there. So as soon as we change the metal, now the currents change. The amount of induced currents change because we've changed to a stainless steel. And now this guy is turning on at 5 and switching off at 6. Okay, again, around like a half mil to mil hysteresis there. But as soon as we change that metal, then we changed our switch on and switch off point. Next guy is brass. So we're just following in that same correction factor here. So this one is number 8. So we'll drop in our brass. Okay, looks like it needs to be closer as well. Right, there's 10, 9, 8, 7, 6, 5, 4 mils, 3 mils it's turning on. Okay, so again, changing to brass now changes the induced currents on there, and it's got to be a lot closer in order to fire on the transistor output of this M18. Okay, again, the switch off point is probably going to be a mil back. There we go. Excellent. Okay, so you can see that brass almost needs to be right on top of it there. Next one is aluminum. Aluminum is number 7. Got that boy in there. And we are now at 3 mils, and it looks like at 2 mils I'm firing on that light. So 2 mils is my switch on, 3 mils is my switch off. Again, it's like a half mil to mil hysteresis there. The hysteresis is there so that if something is chattering, then it's not going to switch the thing on and off. There's a little bit of tolerance between your switch on and your switch off point. You can see that as we change to different metals, then we're going to have to be closer and closer. Okay? If you're looking at something that was copper, then look at this. Drop this guy in there, and this basically has to be almost touching. That's 1.5 mils there, right? So the tolerance between the sensor and the piece of metal is very close now. Okay, so the first, the galvanized steel that we looked at, that was 8 mils away. And now down to the copper, we're now to 1.5 mils away. And probably 2 mils. That's my switch off point. So based on different metals, it's going to change where you've got to put your sensor. So does the object have to be closer or farther away for it to actually pick it up and get nice clean counts as each of those cans or bottles or bottle caps come by? All right, guys, so right now we're looking at page 4-7 on the Allen Bradley sensor manual. Awesome manual, if you can get your hands on it. It goes through all your different types of sensors. Chapter 4 is on inductive sensors. 4-7 has this correction factor here, and it looks for mild steel, you're getting 100% of your operating distance. So for us, that's the 8 mils, right? Then it goes stainless steel, 90%, brass, you're getting 50%, aluminum, 45%, and finally copper, you're only getting 40% of your max operating distance. So our max operating distance for this M18 is 8 mils, right? So if we take a look at this guy, 100% of that is 8 mils. 85 is 6.5. 50% is 4 mils. 45% is 3.6, and 40% is 3.2. So we saw even with the copper, we had to be basically right on top of that thing, right? So sometimes these correction factors work. Other times they'll give you, a window in order to place your sensor so you can pick up each of these different metals. But you can see that as you change different metals, then you're going to get less and less sensing distance out of that unit. Our unit is, this M18 is good for 8 mils, and with the copper, we're down to 40%. And we found that even when we hooked it up, it was down to like 2 mils when we had to actually get the light to turn on. All right, guys, that's it for lab number 3.